Hello, we are very happy to have with us today Professor Kamakoti from the Department of Computer Science and Engineering for this department module on Introduction to Research. He has been a faculty in the Department of Computer Science and Engineering for 15 years and has therefore interacted a lot with a lot of students who have come through the department over the years, and also has a lot of interaction with researchers around the world and the industry. His areas of research interest include software for VLSI, reconfigurable systems design, computer architecture, and secure systems engineering. So welcome to this class and discussion. I would like to begin with asking you, computer science and engineering has been around, for a while, and a lot of people, at least in India, there is a lot of desire to be in computer science and engineering education process. So what are, in terms of research though, going away from undergraduate education, going into research, what are considered as traditional areas of research in computer science and engineering?
So computer science and engineering, as you rightly told, is a most desired field of many people in the country. Reasons are many. If you look at the way man lives today, the actual intervention of computing devices is increasing in a rapid pace. One of the main areas, let us start with one of the main area, which is Internet of Things. Today, the entire health, the entire schedule, everything that a man does could be actually monitored, recorded, for basically providing some sort of service to the person or to actually for other monitoring purposes using devices. So the electronics and basically the compute part of the electronics has become closer to the mankind, and that has opened up several research areas. The traditional areas, if you look, they are hardware, software, applications, and theoretical computer science. In the hardware, basically people were looking at how to make hardware that will work, that can be sold in the market, and specifically they were looking at how much power it will consume, how much weight it will be, and how much heat it will dissipate, to basically see that it is deployed in some environment. These are traditional areas of research when you look at hardware. The second, on the software side, people are looking at how to actually provide certain infrastructure by which people can develop software on the system. So software is of two types. One is the system software, which basically comprises the operating system, which comprises the compiler, and then certain build environments, like for example certain design kits that we call. And a lot of research has gone there, which we call traditionally as software engineering, of how to make tools that can enable people build large-scale software. The other aspect of software is the applications, where you actually build applications that suits different environments. And governing all these three is the theory, which is the foundation. The theoretical computer science basically tells you that if you want to solve such a problem, what is it that you can expect? How much time will it take for a system to execute this particular, to solve this particular problem? So you get some ideas, and based on that ideas you refine your solutions, and before actually you start implementing a solution, the theory basically gives you a lot of insight into how well your final solution could be. So to answer your question, to sum up the answer for your question, there are four major areas of research traditionally, and it continues today: hardware, software, applications, and theory.
Oh, great. I think nicely summarized in that way about what computer science in general is in a traditional sense. In the same context, of course, even in traditional areas of computer science, like in other forms, disciplines in engineering, even in traditional areas, I'm sure there is, the latest, versions of what is happening and how people work on it. But in addition to that, in addition to all these areas and the, cutting edge of those areas, are there areas of research in computer science that are considered recent areas of research?
Yeah. So as I started this conversation, one of the new area of research is Internet of Things. Internet of Things, basically the research there is that I need to monitor something, I need to send some data for whatever purpose it may be, For example, I need to monitor traffic, I need to monitor pollution level, I need to monitor temperature, I need to monitor say tsunami today. Now, how do I sense that data, how do I take it out and then send it to a global monitoring place? I communicate over the network, and then somebody goes and views that data and say, oh, there can be a tsunami, the pollution level is high. So, there should be somebody who makes a decision based on the data. So, this entire notion of Internet of Things has opened up several challenges in the traditional area of research. For example, sensing is an interdisciplinary topic. So, we start now interacting with say people who make sensors. Suppose I am monitoring the structural health of a building, I start interacting with a civil engineer. Okay. When I want to, you have a car which has a smart hybrid vehicle system, you start interacting with an IC engine person to basically understand. So, all these are data collection points, and that is now becoming an interdisciplinary research of how I effectively and efficiently and accurately I capture the data. Once the data is taken, then I need to have mechanism by which I do some local processing. Many times this local, so that comes under the hardware design, right. So, one of the traditional areas, and the challenge there is that I need to process that data with limited amount of compute in. See, I can't put a server at every traffic point. Suppose I am monitoring the data, right,
okay.
Monitoring pollution level. I can't put a server in every signal. So, I need to have some very small devices which can work probably in a solar type of environment, and I need to do some processing. Then after that, I need to send that data to a server somewhere. That is a problem in computer communication. So, that is a big problem in communication. So, because I may have limited bandwidth, I may not even have network connection. Say suppose I am doing a remote sensing in say a high altitude area, I may not even have network connectivity. So, how I gather the data and bring it. So, that is another challenge that is coming up. Now, so IoT is one very, very important challenge. Now, once you get this data, what do you do with this data? So, it becomes a problem of plenty. Now, I have to handle this data, I need to visualize it, I need to process it quickly. For example, if there is a monitoring traffic, I need to tell very accurately within the next few seconds that there is a traffic jam here. If I say 1 hour later, then it does not make sense. So, there is some real time requirement for me to quickly assimilate that data, get to some conclusion about that data, make a decision and communicate that decision out, or make an observation and communicate that observation out. This opens up a vast field called data sciences, right, or data analytics. Now, so that is another field. So, data sciences, data analytics becomes one very important field. So, when you look at that field, now there is a software by which I need to process the data, I need to write applications to actually extract the data, and then this cannot be that just by viewing say millions of bytes of data for me to come to a conclusion is very difficult. Now, I may have to monitor several situations and then come out with some observation, and that monitoring mechanism comes under the purview of what we call as machine learning, right. So, there are machine learning engines who would have studied these patterns over a period of time, and then they will now say, okay, this pattern now is coming, so this should be matching on to one of those earlier things. So, there is a training phase. So, machine learning is another thing that crops up because of this Internet of Things. Then covering all these things is now what we call as the information security. For example, monitoring a pacemaker of an individual is now done by a device which can be remotely operated. So, it takes your heart parameters and it sends over a network and doctor can monitor. Now, if somebody could penetrate into this network, a hacker can penetrate into this network, now he can just go and basically stop the pacemaker. Essentially, you can do a cyber murder today.
Oh, okay.
Right? So, that opens. So, as and more your electronics become close to your heart or close to your body, and it becomes more penetration, its penetration into your basic living becomes more and more increasing, security becomes a major concern. Now, security is a habit. If you take human being, if that habit is not inculcated at the age of 5, you can't inculcate it till symmetry. This is a saying in Tamil. Anjila valayadadu, ambadula valayadu. So, Tottil pazhakam sudugaadu varai. So, these are all some statements you see in Tamil. So, the habit that you inculcate in the age of 5 will be thing. But now, computers are in its, say, around half a century today. Software development started, big software development started late 1960s, even before we both were born. Okay, so in our previous birth. So that's at least now 50 to 60 years old today. Till now, people have not been looking at security in a big way. And suddenly, the security, which is like a habit, has to be retrofit into this overgrown old man or woman.
Okay. Yeah.
And that becomes a big problem. Today, if I ask you, is this mobile phone secure? Right? I don't have an answer. Will my data in this mobile phone be stolen? Or if I ask you a question, can somebody hack and get some personal details from this mobile phone? I don't have an answer. Right? So because the system has so much overgrown, and I don't know how to basically go and certify that it is secure. So this information security, suddenly with the boom of internet, and suddenly people realizing that internet can be used for malicious reasons also, information security is growing up as one of the major areas of research today. So whatever you talk, this is going to be information security should be there. So everything finally boils down to how secure is the solution. Okay. The next thing that has happened over a period of time, so we have covered something on application and something on software and machine learning and all these ends. The other important thing that has come up, specifically in large scale computing, what you call as high performance computing, is that we could not increase the frequency of the processor, clock frequency of the processor. As you see, we are not seeing any processor that is running more than say 3 to 3.5 gigahertz. The reason is that the power is directly proportional to the frequency, and so if I keep increasing the frequency, the power will be so high that it will burn the processor itself, literally burn the processor itself. So people have now moved on from a single core model, a single CPU model, to multiple CPU. So I can't give you 10 gigahertz, but I can give you 4 CPUs each with 2.5 gigahertz, right? So that is possible for me. So now you cannot actually find a processor CPU today with just one core, which is all multi-core. The moment I have multi-core, then one of the important things that we need to research upon is how do I make all the 4 cores work together. So if your program is a sequential program, namely first step gets executed. So suppose I want to add 100 numbers. Suppose I say add the first number to the second number, then to the third number, then to the fourth number. This is a sequential program. Now I need to say, okay, take 4 chunks of 25 numbers each, make the first processor add 25, second processor add 25, third processor add 25 and fourth, and then collect the result and give one answer. So this is the difference between a sequential program and a parallel program. Now parallelization is now becoming another major area of interest, right? So we have to take a program and see how I can make it into concurrent pieces which can execute at the same point of time and give us a result. So in a nutshell, these are all some of the new research areas which are very nascent in stage, and there are a lot of gold mine of open problems for people.
Okay, very nice. That's a very thorough perspective of, very detailed perspective of where computer science is today, computer science and engineering. Maybe in this relation, since you both mentioned traditional areas and modern areas that are coming up in computer science, if you look at the industry, I would like to look at this from, say, the perspective of research students who finish an MS or a PhD degree. What sort of activities that go on in computer science are of sort of more immediate interest for the industry, where if students do research, it's also something that they can see immediate applications to.
So industry today can be broadly classified again based on the areas of research. For example, traditional hardware design. where there is a lot of stress on today on how to make hardware that will dissipate very less power, how to make architecture that can suit different environments today. So one which can do, today if you take a network appliance which takes some packets and route it, it is also a computer. Right? So how do I make devices that are very small and that could be used in millions, for the Internet of Things type of application. So there is a set of people, set of industry which are looking at these type of hardware designs of low power, high performance hardware, and they are looking at different models of computation. Today there are notions of what we call as approximate computing, stochastic computing, non-Boolean computing. So different computational models are there, and the research labs within these core industry have started looking deeply into this. So this is one line of that. Then the second line is that the systems are becoming very complex. So how do I model a complex system, right? And then how do I verify it is working correctly? So there is how do I make a hardware with lot of complexity. So the CPU that was taught for an entire semester in my BTech curriculum in 1985, today I teach the same thing within the first week. Okay. So that's a bigger challenge here, because history cannot be forgotten, but at the same time, the progress is so rapid that what I learned for an entire semester, I need to teach it within one week here. So essentially, the systems are becoming more and more complex, and how to model such systems, how to verify their systems. So that is another area. So hardware, if you take, there is hardcore design and hardcore modeling, and these two have lot of open problems and lot of job opportunities. So this is one set. Now when we come to the system side, that is the operating system, there are very few groups which work on operating system. There are very few individuals in the country who can actually go into a kernel and come out with modifications to the kernel. There are very few across the globe who can do. Few in the sense, in terms of percentage, it will not even cost 1% of the total computer science engineering people whom we graduate, right? So because it's very, very complex. So if people start working on these type of issues like kernel level and the compiler basically optimizations and a lot of system programming stuff, there's a lot of potential for them in terms of going into very core research jobs, be it a faculty position or an industry position or even a government research establishment position. So that is also very, very interesting problem in terms of research, in terms of publication, in terms of livelihood, everything is a very good thing. And the next thing is applications. Today, application wise, if you look, there are two ends. One is an elephant, namely data sciences. Data sciences today spawns between anywhere from, if we have 16 departments in our institute, every department has a data science related problem. And that is proof that we have a data science laboratory today, which has 22 or 27 faculty members across all the 16 departments we have today. So that's a massive field. That is one end. Another end of the spectrum is we have this IoT type of devices. In the IoT, the memory will be very small, so I can't write large scale programs. I need to have very effective coding, efficient coding techniques and stuff like that. So writing those type of small programs on the devices, that's also a very big, today, that's a big skill and that we need to look into it. So, that is from the application side. So if you look at hardware, if you look at system software, you look at applications, these are all the big research areas. And of course, on the systems application side, writing these type of parallel programs also is a skill, and very, very few people across the globe has this type of exposure. There are very few universities who even offer such type of parallel architecture and parallel algorithm courses, right? So these are something that are of great research interest here. And if somebody aspires to do that, if they take any one of this area and spend say 2 to 3 years and demonstrate to the world that they can think new, publish a couple of papers, write some sort of software, I think they have a great future in front of us.
Okay, that's I think a very good perspective for income students to consider.
Right.
Now, I see over 15 years you've seen several students come in and graduate. Not I mean maybe directly in your group and also around in various groups and so on. In your opinion, I mean, see, there are already some metrics that people use for gauging, how progress in research is going on and how successful students are in research. In your view, what are the parameters that you would look at to gauge success in research that maybe students should also consider looking at?
Right. So, if you ask this question, if you had asked this question in 2001, then 2005, 2010, 2015, my answers would be different.
Okay.
2015, the answer or probably 2020, the answer is that today, see, those days I could very well say I am a hardware engineer and forget about everything else. And things worked for me. Like, I could have a career based on hardware engineering, just hardware. I could go to a company which would look only at hardware. And I could have a successful career, but that career would have been a short stint of say 6 to 7 years. Now after that things started changing. Today I can't say I am a hardware engineer, okay. Everything today is cross layer, okay. So if you look at traditional computer science, it will be there for any device you take in computing. I have something called digital circuits, and on top of it, I am talking about a digital computer. I have a digital circuit, there is a microarchitecture, then an operating system, then system software, then application. So this is stack. For me to even go and tweak some parameter, for example temperature control at a circuit level, I need to know the entire stack. I should write a thermal aware compiler, I should have a thermal aware operating system, I need to have a thermal aware microarchitecture, I need a thermal aware digital circuit. So anything that I want to do anywhere in computing, I need to have the entire knowledge of the stack, and then only you become a full person. And if you don't have that knowledge, then sometimes it becomes quite shaky. You can be bowled over at some point of time. So my sense of success today is if a student is able to do a research work where he demonstrates that whatever he has found out, in whichever layer, that 5 layers I told, right, digital circuit, microarchitecture, operating system, system software, application. In each of those he would have made some enhancement, but he should now demonstrate that this is, well, there is a synergy of this and it will be effective in all the 5 layers, and he is able to argue it and bring it out. I think that is success with respect to and that is also the challenge, right. So today the challenge essentially comes. So normally I give questions in comprehensive Viva and typically NSEMs to design a thing. So they will give a very good answer, but it will take say $2 billion to implement. Okay, so that's not engineering. So I need to make a hardware, or I need to make a system that could be effectively implemented. That effectiveness is just not performance, but it's also cost and sellability in the market. So I might have a very good architecture, but it costs that machine costs $1 billion. Probably one fellow will buy it. Okay, so then it will not be successful. So to have that notion of cost performance and have the notion of the entire stack, right, and it should be feasibility. That is very, very important, and that's how I feel that a particular research is successful only if it addresses, at least in computer science, it addresses this spectrum.
Okay. And now, I mean, in that context, in terms of in the context of say being successful as a researcher and so on, when I think in general there is always an expectation, there's always this feeling that when somebody does an MS or a PhD degree, they are now specialists in that area, and maybe that restricts what kind of positions they can go for. And so that's always a concern that students have when they pick up an advanced degree in any field. In computer science, what sort of positions do students who finish MS and PhD degrees tend to get?
Okay, so I did. So let me just I did a PhD in theory, absolute theory. I have not done anything on systems, but then I got a job. I worked for 2 postdocs and they were more or less theory, but then I got a job in the industry which was on processor verifications, completely hardware. Then I came back and I did VLSI here. Today I also consult for a financial bank, and I am able to do some IT activity there. So if you take, essentially we started off with theory, but we are able to do hardware, we are able to do applications.
Okay.
So just looking at myself, my choice of taking theory that time did not actually restrict me explore all these opportunities.
Okay. Nice.
Whether I am successful or not, we have some more years to tell that. But today I don't feel some handicap because I took theory that day. So that's the reason why I put myself as a case example here.
Okay.
I think computer science is very broad. Actually, I've seen very good software engineers, even from our own institute. They are chemical graduates. Okay.
Okay.
And interestingly, 3 of big shots I know in the field of software who have been vice president of software that goes on to Amazon. Why Amazon or Yahoo or this type of sites, right? If you put there, within the next few seconds, there will be 1 million hits or something. So whether a software is working or not will be known within the next few seconds. By the time you wink your eyes 3 times, your software stability will be known. So these type of projects people have handled, and all of them are non-computer science people. So if non-computer scientists could survive in a bigger market, I think somebody who has reasonable introduction to computer science, irrespective of what they have done, databases or whatever they have done, I think will certainly have a very good future there. So at least from computer science point of view, people need not really worry what area.
Okay.
But there are certain core courses like data structures, algorithms, programming languages, computer architecture, operating systems. These core courses are there. Basically the language of computer science, right? Basically automata theory. These courses, people either in the undergraduate level or in the postgraduate level, they should be thorough with. And what I mean by thorough is, there are some very standard textbooks for each one of them. And NPTEL has a lot of lectures, people have to access it. And there are very good problems. I don't know about other fields, but one thing very interesting about computer science is all these books have very interesting problems at the end, exercise problems. And people have to work out these exercise problems. Whether you are a teacher or a student, it is a must that you work out all these exercise problems before you start teaching or you start researching. If those things are done, then that foundation will be strong, and then you can explore anything. So that worry that if I take data sciences, I may not able to do anything else, it's all unfounded.
Okay.
If you have this foundation, anything you can learn and develop within a few years.
Okay, great. Yeah. So this is about the people who, we just spoke about the people who are just leaving the department with a postgraduate degree.
Yes.
Now, if I step back a bit and look at the people who come in to, yes, to your department for a master's or a PhD degree, in general, do you see them facing any specific kind of difficulty for them to adjust to research in computer science and engineering, and if so, what are your suggestions on how they are supposed to handle?
So my suggestion to all people who are entering computer science department in general, which I have been coordinating the same research methodology course quite some time before, and I insist during the department modules, and I tell now, there is one theory, like if you don't know the language in which you can communicate, you can think, right? You cannot even think, right? So even if I start thinking, I think in some language. So if I want to think about computer science concepts, the language of computer science should be there in your mind. Then you can think anything about computing. Now what is this language of computing? It is basically formalism, right? Suppose the problem that I see even with my students who are about to graduate is that if I ask them to describe something from LKG to +2, they start with LKG entrance, then +2 final exam, then some 8th standard half yearly, then 3rd standard quarterly. The organization of ideas is not it's very, very zigzag. So what it means to organize that idea, suppose I ask you to write a research paper or present something informally, the idea should get organized, and the way you can do it is to basically learn the language of computer science. And I strongly suggest that there is a course called Discrete Mathematics. Discrete Mathematics, I think there are 2 offerings in NPTEL. One offering is by Professor Kamala Kirtivasan, and she has done it so nicely that she will write line by line and repeat every line twice, and that type of course. And she also has a book, her own book, which you can use it, and it does excellent problems. And there are many books in Discrete Mathematics also. Take one book, good book, and listen to these type of NPTEL lecture and get yourself very thorough with Discrete Mathematics. There is another book by Knut, who is father of computer science, and he has written that's called Concrete Mathematics. So these type of Discrete Mathematics and Concrete Mathematics, if people look into it, just solve at least 20% of the problems in some of the standard books there. That will give them the organization of ideas. So I want to write a proof. How should I go about? What sort of proof technique should I use? How do I go? Stepwise refinement. All these things will come. The moment you have that clarity of thought, then I think it becomes very easy. Whichever. So this is one problem which people face, and somehow when we all did our PhD program, we used to listen to our guides. So my guide was Professor Pandurangan. He said, do all these things. We did all that 300, 400 problems in standard book or something like that, and we all cleared. Now that type of diktat is not working out with our modern students. So one of the things, though we don't want to take a parental role or a dictator role and say do it, we will now request them to go and look at these 2 books and study this. This language of computer science has to come.
Okay.
If it comes in, then any subject will become easy, because you know how to think. Then you can think about anything. Nothing is rocket science after me. This is one fundamental problem. So communication skill, in this conversation, so I would have made say some hundreds of grammatical errors, but meaning we are able to convey, hopefully, right? So this type of real Shakespearean English and all we don't need. We just need them to write the proof clearly, write the concepts clearly, explain the concept clearly in the language of computer science. These type of training in Discrete Mathematics and Concrete Mathematics would be very helpful. NPTEL has made a great step towards Discrete Mathematics, and Concrete Mathematics by Donald Knuth book they should follow. This is my general prescription for anybody who wants to
great. That's very nice. In any other engineering discipline, I mean, especially where there's a lot of experimental work, I think a lot of people talk about there is the atmosphere in the group and how it impacts the research student, and therefore the meetings the student has with his other group members and the meetings that he or she has with the guide is a very important aspect. Along similar lines, in computer science and engineering, it may be a bit of a mundane question, but how often do you think students should be meeting their guides, and what sort of an interaction should be there?
More than meeting the guides, meeting the peer group is very, very important.
Okay.
And then having an ear for everything is also very important. They should be very keen on observing. For example, I did a course on distributed computing with one professor, Muthukrishnan of our institute. He retired now, but so the first quiz, I couldn't even understand what he was telling. Then I went to him and asked, sir, I don't know how to handle your subject. Though I got reasonably okay marks, but I'm not too happy with this thing. Then he said, go to Adyar Signal and see how the traffic, he was talking about distributed computing. Go to Adyar Signal and see how traffic is moving here and there, right? Observe it for 2-3 days, then you will understand more about distributed computing. It's true, actually it was true, right? So how coordination happens, how distributed coordination happens, how clocking, how signals work, what happens if signal is not obeyed, what happens if there is a delay, what happens if signals fail. So many things talk about many coordination problems in the real distributed computing sense. So the observation also is very, very important. So I still believe, so now I have a team of around 40 students from BTech, MTech, MS, PhD put together, and then we have 4 faculty in our lab. Each one have something. So we have around 100 to 120 people in the lab, and that is very, very good. So almost 2 students review their paper each other and make our life very simple. And we also now have to scale, because we can't say, when we did BTech, I think it was 20 to 25 in a class. Today we are 3 times the thing. Our MTech programs have grown, our research areas have grown, and there's so many projects also. So we, as a faculty, the amount of time we can spend on a student has also decreased. But how do we compensate for that is to have a larger team, and the team members interact, and when something comes up to you, it is after a lot of refinement there, and I have seen that. So when today I need not micromanage MTech person if he is willing to work, because the PhD student will actually micromanage him to a large level, and now I have to macro manage him now. So peer group is very important. Going across boundaries and basically talking to the next team, understanding what is happening there. Computer science is all about applications. Today we exist because you guys have given us problems. You guys are solving problems on me. If I don't have a user, computer science would have gone, right? So it is a user-grown field. So people have to start looking at those type of things, and that is very good. And specifically in our institute, with this interdisciplinary stuff that has come, actually 4 or 5 interdisciplinary students are in our lab today, and that is creating lot of more exciting problems. So why I am mentioning here is that you talking to your peers is much more important than talking to your guide. But at least once in a fortnight meeting the guide, and also sending some daily reports or weekly reports saying this is what I have done. Even if you have not done anything, I didn't do anything. Okay. So that will keep the whole.
Okay. So I would like to conclude this discussion with what are your words of advice for anybody who is aspiring to do research in pick up a research degree in computer science, or get into a research degree in computer science.
My advice is that we need to work hard. Specific advice that is for any general. Yes. Right? So today, as a professor, my working schedule is close to 16 hours a day. So the student, I expect him to work double the time. So go to sun god and say extend 6 hours and make it 8 hours and make it 32 hours a day. No, work as hard as possible. That is very important today, because the competition is very high. If you look at universities across, if you are working on a problem, there are at least today 10 groups which are working on the same problem. And so this is survival of the fittest. And they all send to the top tier conference, and the fittest one goes in. And if you miss one deadline, there will be 3 fellows at least who would have published in that area, and you are gone, your problem is gone. So that race is there always. And so you have to be prepared to work very hard and to establish yourself. And then the next thing is teamwork is also very, very important. That should start from day one. Work in a team to share ideas and be ethical about it. Because today, if you look at any of the major universities across, a single author paper or student and that author is all gone today. If you take some really seminal papers, there are at least 4 to 5 authors. Right? So this all comes out of some large scale collaboration. Those are exciting areas. So teamwork is very important. And then my traditional advice of getting your formal theory correct, your concrete and discrete mathematics very clear, that is also very, very important. Computer science is a rapidly changing field. So if you think of a problem today, within 3 years you don't solve, it becomes obsolete at the time you submit your thesis. So you have to be on your run. Even I am not too comfortable guiding a PhD beyond 3 years, because the original problem you would have taken would have already become obsolete by 3 years. So there is a big change in field, and lot of things, especially in computer science, is with the industry. So if I get a tool that I am working, this tool is 5 years old. They would have tested for 2-3 years and then released the alpha version to you, and so the tool is already 5 years old. So to keep in trend with the pace of the industry and making it relevant needs a lot of hard work. And so finally it's all hard work plus team spirit plus good foundation knowledge.
Okay. Thank you, Professor Kamakoti. It was
Thanks
pleasure
a lot,
having you.
Pratap. I think this is a very interesting conversation.
Thank you.
And thank you for selecting me from
Oh, not at all.
computer
It's
science
our pleasure
department.
to have you here. Yes, certainly.